The MOSFET, history, evolution, and how it works. Introduction. In the vast universe of electronics, one component stands out for having revolutionized the way we build and power modern devices, the MOSFET, or metal-oxide-semiconductor field effect transistor. From smartphones to solar panels, from laptops to industrial machines, MOSFETs are everywhere. But how did we get here? What makes this component so special? Let's explore the history, evolution, and functioning of the MOSFET. 1. The origins, from vacuum tubes to transistors. Before the MOSFET, electronic circuits relied heavily on vacuum tubes, large and fragile glass devices that controlled electrical signals. Though effective for early radios and computers, vacuum tubes had major drawbacks. They were bulky, consumed a lot of power, and generated a great deal of heat. Everything changed in 1947, when John Bardeen, Walter Brattain, and William Shockley at Bell Labs invented the first bipolar junction transistor, BJT. This invention marked the beginning of the semiconductor era. Transistors could amplify and switch electronic signals with much greater efficiency and in a much smaller size. Still, BJTs had their own limitations. They used a current-based control mechanism and were relatively complex to manufacture in large numbers. Researchers soon began exploring alternatives based on the concept of field effect transistors, FETs, which had been theoretically proposed earlier but were not feasible with the technology of the time. 2. Birth of the MOSFET. The breakthrough came in 1959 when Daewon Kang and Martin Atolla, also at Bell Labs, developed the first working MOSFET. Their innovation was the use of silicon dioxide, SiO, as an insulating layer between the metal gate and the silicon channel. This design allowed the device to be controlled by voltage rather than current, dramatically reducing power consumption. The term MOSFET reflects this structure. Metal, the gate terminal, originally aluminum. Oxide, the insulating layer, usually silicon dioxide. Semiconductor, the silicon base that conducts or blocks current. Their work laid the foundation for the integrated circuit, IC, revolution and the future of digital electronics. 3. Evolution and miniaturization. In the decades following its invention, the MOSFET underwent continuous evolution, both in performance and manufacturing. One key milestone was the introduction of CMOS, complementary metal-oxide semiconductor, technology in the 1970s. CMOS combined N-type and P-type MOSFETs to create logic gates that consumed almost no power when idle, a major advantage for battery-powered devices. Meanwhile, Moore's law, an observation by Intel co-founder Gordon Moore, predicted that the number of transistors on a chip would double approximately every 2 years. This prediction drove intense innovation in MOSFET miniaturization. From micrometers in the 1980s, MOSFET sizes have shrunk to nanometers today. Modern processors now contain billions of MOSFETs, each one smaller than a virus. With miniaturization came challenges. Leakage currents increased. Short channel effects made precise control more difficult. Heat dissipation became a growing concern. To address this, engineers developed advanced structures like FinFETs, 3D MOSFETs with vertical channels, and explored new materials like high-K dielectrics and metal gates to replace traditional silicon dioxide and polysilicon. For how a MOSFET works, the basics. At its core, a MOSFET is a switch that can turn current on or off based on the voltage applied to its gate. Let's break down a basic N-channel MOSFET. The MOSFET has 3 main terminals: gate, G, drain, D, and source, S. The channel between the drain and source is made of N-type or P-type silicon, depending on the type of MOSFET. A voltage applied to the gate creates an electric field, which either allows or blocks current flow from drain to source. In an N-channel MOSFET, when no voltage is applied to the gate, the path between drain and source is non-conductive. But when a positive voltage is applied to the gate, it attracts electrons to form a conductive channel, allowing current to flow. In a P-channel MOSFET, the behavior is reversed, a negative gate voltage enables current. 5. Types of MOSFETs and their uses. MOSFETs come in various forms, optimized for different applications. Enhancement mode MOSFETs, these are the most common. they remain off by default and require a gate voltage to turn on. Depletion mode MOSFETs, these are on by default and require a gate voltage to turn off. They are less commonly used but still valuable in specific applications. In terms of channel type, N-channel MOSFETs are faster and have lower resistance, making them ideal for high-speed switching. P-channel MOSFETs are typically used in complementary circuits alongside N-channel types. Applications: MOSFETs are used in computers and microprocessors. Every logic gate is built from MOSFETs. Power electronics, used in motor control, DC-DC converters, and power supplies. Audio amplifiers, due to their linear characteristics. RF circuits, especially with LDMOS, lateral diffused MOSFETs. Automotive systems, electric vehicles rely heavily on power MOSFETs. 6. Modern challenges and future directions. As MOSFETs approach atomic scales, classical physics begins to break down. Quantum tunneling, thermal effects, and variability in manufacturing limit further scaling. To keep up with performance demands, researchers are exploring gate-all-around (GAA) transistors, carbon nanotube and graphene transistors, spintronics and quantum devices. At the same time, wide bandgap semiconductors like silicon carbide (SiC) and gallium nitride (GaN) are being used to build MOSFET-like devices for high-power, high-frequency applications. These materials offer faster switching and greater efficiency, especially in electric vehicles, industrial systems, and renewable energy. Conclusion: from its humble beginnings in the labs of Bell in 1959, the MOSFET has become the backbone of modern electronics. It is the invisible force that powers your smartphone, drives data centers, and enables AI computations. Its journey from a theoretical idea to a nanoscopic marvel is a testament to human ingenuity and the relentless pace of technological evolution. And while we may eventually reach the physical limits of traditional silicon MOSFETs, their legacy will live on, both in the circuits we build today and the new frontiers we'll unlock tomorrow.